Hi, it's me again. Greetings from Brussels. Brussels has just seen and it's still ongoing actually, the party around the Pride Festival, the Brussels Pride. They just marched through my street and it was quite amazing. So I came back from that and I want to do something short, something nice on sort of, yeah, what I want to do with all these videos here is sort of bring back some fun in terms of interpreting quantum mechanics and sort of reconciling a very classical framework with the what I would call the statistical determinism that comes from the modern day interpretation of quantum mechanics. So I want to go back actually to an experiment or an explanation, which I did a bit in 2018, a sort of a classical explanation of this very famous Mach-Zehnder interferometer experiment, when you let you know not a light beam go through, but a light beam, one photon at a time, and then how to explain sort of how all these photons end up at one detector instead of the other. I want to explain that in terms of a very classical physics combined with what I always say actually. Physics is classical physics plus the Planck-Einstein relation. The idea that things are quantized in nature. We have photons, light particles, and we also have matter particles, and they all pack, so to say, um, one or more units of Planck's quantum of action. The references I'm going to make is, yeah, an MIT EDX course I followed on quantum mechanics. I never did the exam because, well, after 15 chapters, I was basically being told sort of, just shut up and calculate, where I was going like, calculations are fine, but what's the reality behind the wave function of a photon? Does the photon have a wave function in the first place? So I want to talk about that now, and I'm going to do it with some explanation of what Feynman has to say about it in his first two of the 3 volumes on physics, and especially in volume 1, what he has to say about the polarization of light. So let's get on with it. I said it's really sort of a fun and a freewheeling analysis. With the basic objective is that I want to correct some mistakes I did previously in papers where I gloss over things, and at the same time, I encourage you to sort of see that, hey, this makes sense, and this is indeed sort of an approach where we can think about what these base states are in quantum physics when you talk about photons, light particles. In a classical analysis, we will analyze not the light that we see. We will analyze a monochromatic light, where the electric field, we know light is an electromagnetic oscillation, oscillates at a very definite frequency, which is a color in the visible spectrum and a, how would I call it, a color in the invisible spectrum as well, X-rays or whatever. So we know then that the classical view is that we have that here, is that we have an electric field vector which oscillates with a certain wavelength and a certain frequency, and we can couple that to the time. The frequency is 1 over time period. And we know that that's a wave, and we also know that this is very much neglected, that an oscillating electric field vector comes with a magnetic field vector, which is often neglected because analysis will show the electric field vector, but we know that Maxwell's equations in free space, when we have no charges, just a propagation of an electromagnetic wave, Maxwell's equations boil down to two only, because the current is zero, there are no charges. And yeah, here I put also the fact there is no such thing as a magnetic charge, there's only electric charge, so I don't put that equation either. And so what we have is that, Maxwell's equation in free space, when we are talking about the electromagnetic wave propagation mechanism only, reduced to these two equations, where we basically, the magnetic field will change in time, and the electric field will change in time. And so the propagation mechanism of an electromagnetic wave is basically that, when the electric field changes in time, mathematically that amounts to some kind of flux through a surface or through a loop, through the loop, literally. We have a loop, surface, and electric field vector goes through that surface or through the loop, and its flux changes, and that will lead, this is the genius of Maxwell, to some change in the circulation of the magnetic field vector around the loop. So we take a line integral of, in this case, the magnetic field vector around that loop, and we will see when the flux changes, that circulation will change. And that circulation that changes, of course, we can think that will also cause some change in the flux of the magnetic field vector, and that in turn feeds into what I put there, some circulation of the electric field vector. So we have a propagation mechanism, and that's classical mechanics. And yeah, we often tend to forget about the magnetic field, and we need to see the two of them together. It depends really on your frame of reference, whether you sort of see, more of an electric effect, electrostatic effect, or a magnetic effect. In the relativistic analysis, we know that half of the electromagnetic field energy in that, electric field oscillation, well, half of the electromagnetic field energy will be in the electric field oscillation, that E, and the other half will be in the magnetic field oscillation. That's an analysis I did in a previous video, the energy in a field. Here. Yeah, the energy density of the field, and then the Poynting vector. We know the energy density in the field is equal to half times 1/2 the squared electric field vector. We know that's an amplitude, and energy is proportional to the square of an amplitude in an oscillation. The electric constant makes the units come out all right, and we have also, the magnetic field vector. We know they are both related. The electric field vector divided the magnitude of the electric field vector divided by c will be the magnitude of the magnetic field vector. So we know that the energy density of the field is split indeed over half what we can view of as the oscillation, the energy in the oscillation of the electric field, and half the oscillation in the magnetic field. Kind of screwed up. So let's consider now, move away a bit from this classical analysis, although it's still very classical. Einstein wrote his paper on the quantization of light in 1905. He never got a Nobel Prize for it. He got his Nobel Prize for the Brownian motion. It's kind of sad. I'm not going to gossip about the way Nobel Prizes are being awarded. But yeah, Einstein did not get a paper for his theory on the quanta of light, but they are real. So we can consider one photon. One photon in light, photon will also sort of have, it's a point. Let me make that clear here now. What is a photon, right? A photon is a field that it's a dynamic field, so it travels in space. So it's dependent on the x, y, z components of that field depend on time, and it's a special case of a field because the electric and magnetic, when you decompose it in electric and a magnetic field component, it's going to be 0 at every point x, y, z at time t, except when the photon happens to be at position x, y, z at time t. So the funny thing is that you have, oops, take another color. When the photon is here, we can kind of make a composite E plus B vector here. And the next moment, that's going to be, well, photon is no longer going to be there. It's going to be here, for instance, where both the electric and the magnetic field vector are 0. And now you will say, where is the energy? Well, the energy is in that complete oscillation over that wavelength. And then you can apply a relativistic analysis and say, like, because that photon is moving at the speed of light, in the end we do think it's it's at one point only, and the whole energy that is in this oscillation indeed sort of gets absorbed or emitted by an electron as a unit. So the thing is, let me clean up the sheet. What about energy conservation? Well, I said that it's sort of like, that's the nice thing about the combination of classical physics with the Planck-Einstein relation since the beginning of 19th century. It combines. We cannot think. A photon will always be at one place at any time. So if it's not here, if it's not here, if it's not here, then maybe it's there or the other way around. And it will pack a 1 unit of Planck's quantum of action. So you do need that idea of a cycle time and the idea of quantization. A photon was the first periodic phenomenon, linear periodic phenomenon, that was discovered. And then the Broglie's invention was really that, well, I'm not going to go into detail on that, is that, matter particles also are, oscillations. Instead of linear oscillations, they're orbital oscillations of charge. So we do have a force, we do have an electromagnetic field. They're like, perfect currents, superconducting currents. So let me not dwell on that. Maybe I should dwell on it. It's you can write it in sort of in terms of a complex because that's what wave functions are about. They're complex numbers. Is that you can sort of have a composite vector E plus B. Here in this case, we have this E, we have this B, so this composite E plus B is equal to that. Here in that case, it's actually 0. Here we have something smaller. So we have sort of a composite vector, which you can write as the product of 1 minus I times the electric field vector. But you do need to remember that you need to add like a sine or a cosine, depending on your phase, to sort of see that this magnitude of this vector is going in and out. It goes to 0 and then goes to the other side and comes back. Chinese, you will say. Yes. It's not Chinese for me. I don't want to repeat too much from previous videos. You can think about these things in terms of, the average field strength, which is 2 divided by pi, and then, we can work with this reduced wavelength, and, we can do so many things. We can think about a photon hitting an electron and define structure constant as some kind of a ratio between the surface areas, the surface of an electron, as we have some charge spinning around an empty center, etc., 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 etc. But that explained in previous lectures. So let me move on and go back to what we think a photon would be. If we consider one photon, if we think of a light beam being made up of photons, the quantum of light, and I said we can have many photons at the same spot in space, then you need to think about sort of how can we relate, when we have this electromagnetic wave, how can you relate that to one photon, to one quantum of light? And that's where you talk about polarization then. When you have an electromagnetic wave, and we have a reference frame, then we know that electromagnetic wave will be actually an electromagnetic oscillation, which is perpendicular to the direction of propagation. So we have E and B being perpendicular field vectors to the direction of propagation. So we have an X vibration. Well, here sort of let's call the direction of propagation the Z direction. So we will have an X and a Y direction, but specifically for the E direction, for the electric field direction, well, it doesn't necessarily need to be in in this direction, could be in this direction or in this direction or in any direction. So we will have an X and a Y direction, or if you want an X and a Z, that's a mathematical convention where you put your X, Y, Z actions. But any any oscillation of the electric field will have, a component in the X direction and a component along the Y direction. And that's what sort of in that paper here, the MIT EDX course, they call the component along the X hat direction to make sure that we are indicating the axis, and a Y vibration along the Y hat direction. So the conclusion that you have then, and that's something that I didn't make clear in previous papers, is that actually, one photon, when you think of one photon, you know that it will always be linearly polarized. I will nuance that statement in a moment, but it will go in this direction, or in this direction, or in this direction, electric field vector, with the magnetic field vector following by a phase difference of 90 degrees, or pi divided by 2. And that's what I show here. If this is sort of how should I put it, the direction of the beam is pointing inwards of outwards out of this notebook, then it will be either something like this, or something like this, or like this, can be anything. So these two states show that the component in the X direction is 0. The component of the electric field in the Y direction is 1 or -1, because the field vector oscillates up and down. multiplied, of course, by some kind of amplitude, which depends on the energy of the photon. You know, we have green light, red light, X-ray light with very different energies. So we just kind of normalize it to 1 here. But yeah, if it's sort of, you know, oscillating the electric field vector in this direction, then X and Y components will be equal to 1 times the, well, the amplitude or the absolute value of the electric field vector. Like this here, we can play then 1 over 2 or minus 1 over 2, and etc. But the basic statement I want to make here is that you know, when you really think things through, it's you know, photon is essentially, you know, a plane polarized. But you will say, yeah, but this thing can you know, spin around, right? So we can add spin to the thing. And yes, you are right. I will talk about that. But basically, circularly polarized light, when you think of it as being composed of individual photons that have a certain phase, which they oscillate up or down, is linearly polarized. So it's only when you start to think about, you know, an X vibration and a Y vibration that are not in phase that you get, you know, elliptically or circularly polarized light. So again, how does spin come into play then? Well, when you're really considering here this, you know, an oscillation in one direction, then you need to sort of think, well, okay, we can imagine that this thing would you know, spin around this direction, or that it would spin around in that direction. So then we add spin, which can be 0 or +1, right-handed, or -1. So the spin state, and this is something really crucial, which I completely neglected or I wasn't aware of, is actually the spin state of the polarization state. So the polarization state can be, you know, anything between these two, you know, like this, that, whatever. But it's a plane polarization state that we can spin around. Now that spin state of a linearly polarized photon, and that's also where relativity theory comes in, you know, in my reference frame, I will see spin. In another reference frame that is spinning around, you know, the photon that is spinning around, you know, the spin will be 0. So the spin +1, minus, or 0 states, they don't change the color. I should put this between brackets because color is associated with the visible spectrum, but they don't change the energy or the frequency of the photon. So that's what I write here again. The spin state of a photon is the spin state of the polarization plane. So now we, because I promised to talk about that one-photon Mach-Zehnder experiment. What happens when light goes through a polarizer and you do these experiments with the beam splitters and you see that, you know, as Schwiebach, the MIT professor who gives the EDX course on quantum mechanics says, you know, we can only explain it by with wave functions. Is well, maybe not. What's a polarizer? You know, beam splitter uses a polarizing material. It has an optic axis. Why does it have an optic axis? Because its material is not isotropic. Polaroid is a commercial product. I forgot the name of the group who posed it. But it's basically Polaroid. You know, the stuff you use in your camera and whatever is a synthetic material, plastic, doesn't look like plastic, sheet made of, and here I'm having some fun, iodoquinine sulfate or herapatite, which, you know, that's a crystal structure, a lattice structure, and you can see from the chemical formula here, it's quite complicated. 60 carbon atoms, 84 hydrogen atoms, and nitrogen and oxygen and silicium and whatever. Embedded, sorry, that's sulfur, that's not silicium. Embedded on top of that in a transparent nitrocellulose polymer film, which is plastic also, which is a polymer, you know, N a chain of N very complicated molecules, again, carbon, hydrogen, and nitrooxygen, nitroxide, sorry, and oxygen. So these are needle-like crystals. And what's so particular about them is that these needle-like crystals um, are aligned during the manufacturing process by applying electromagnetic fields. So you have very long, you have a crystal structure, but the crystals are needle-like and they're in a film and they're all aligned. And I quote Wikipedia now, any varying electric field, you know, of an incoming electromagnetic wave in direction that is parallel to that line of crystals will cause a current to flow along this line. So we have these crystals and you know, if the electric field gives a push, show that. How does a photon give a push on an electron, right? I hope I have it here somewhere. Yes, we have incoming light. We have an electron here in an electron orbital around, you know, proton or whatever. And that electron, you know, we have an electric field, which may at that point of time, depending on the strength of the electric field, when the photon is here, if the electric field is zero, then of course it won't interact, right? So in this case, it won't interact, but you know, if we have this, the electric field vector is huge, then the electron in that electron orbital will experience an electromagnetic force, which is given by the Lorentz force, the electric field vector, magnetic field that comes with it, and yeah, that electron will be disturbed in its state of motion. What does that mean? Well, it will jump to another atom. It will jump the line, or it will go to higher energy orbital, or all kinds of things. But there will be what we call in classical mechanics a current, an electric current. So that's what happens. So the electrons moving. While the varying electric field of a photon or of a wave, you know, will in direction that is parallel to the line of crystals cause a current to flow along this line. The electrons moving in this current will collide with other particles. They will jump from one atom or molecule, I would say, and they will, yeah, they will come back to their equilibrium state by emitting another photon with the same energy usually, and that will the light will be emitted backwards and forwards. You saw that sort of move of the electron on the page I showed, and you know, so there will be light that will be re-emitted. So the energy in the incoming light photon is absorbed and is then re-emitted as light again. This will cancel the incident wave, causing little or no transmission through the sheet. Get this, the incoming photon or electromagnetic wave will not be transmitted through the sheet because, you know, its polarization is in a direction that is parallel to the line of crystals that is parallel to sort of what I show here. Polaroid has an optic axis, and only the light that is that has the photons that have a polarization that is more or less in line with that vertical optical axis here. Those are the photons that will get through. Component of the electric field perpendicular to the line of crystals can only cause small movements, and they cannot move fast. So that means there will be little change, and so that light will be transmitted as part of the light wave polarized perpendicular to the crystals only. You can look it up. The point, and I put that here also, is let me move that to that. It's not sort of a 1-0 story, as a quantum physicist would like you to believe. Unpolarized light, some gets reflected, some is more in line. You need several layers of such material to come to a clearly polarized state. I can't clean up my sheet. It's kind of sad because I wanted to do it. The point to note is that, for photons, no photons get lost. They are either being absorbed with the emission of another photon, or they are being transmitted in the state they were in before going through, or perhaps with some very little interaction. But photons don't get lost, and that's where that one-photon Mach-Zehnder experiment, the way it's usually explained, often goes wrong and becomes like meta-magical or mathematical, if I may call it like that. You will say, of course, in Mach-Zehnder interferometer, we don't have a Polaroid, we don't have cellophane, we have a beam splitter. Yes, we do. Beam splitters are of two kinds usually. This is the one that is used in the Michelson-Morley experiment, a half-silvered mirror, which is basically a sheet of glass or plastic with a very thin coat of metal, such as aluminium or silver, which is deposited from an aluminium or silver vapor. I don't know how this works exactly, but let me go to the principle here, on where you have a cube, the cube design, two triangular glass prisms where you have a beam of incident light, and the principle is, well, some of it will be reflected, but let's say all goes through this little reflection, and then 50% of the line will be reflected at the the border, the surface area of the two prisms, and the rest goes through. That's all very mysterious, but not so much when you think of the material of which these prisms and materials are made of. It's crystal structures. We have degrees of freedoms in terms of how the electrons can oscillate or jump between one atom or a molecule at a time, and that explains it. So this is then the setup for this famous or infamous Mach-Zehnder experiment with one photon, and I will come to that now. I just want to say on this cube design, there's many designs. The basic principle, which you need to understand before I go to the explanation, is that indeed you have light, non-polarized or circularly polarized or whatever, and we need to understand that we have, many photons on top of each other, or photons arriving in some kind of sequence, and they will have a plane of polarization, which may have spin or not, but they go through this thing, and they come out as photons with a fixed polarization plane, like this or like that. So here again, I take these. I know the source because I need to pay attention after the censorship I had when trying to debunk some of the lectures of Feynman, is that I quote my sources here, and this comes from Wikipedia. These prisms are available with divergence angles, yeah, from less than 1% to about 45%. The thing you need to remember is that we have two separate beams here that come out with orthogonal polarization. Okay, I'm going kind of quick and slow at the same time, I guess. Let's go to the explanation of the experiment. I sort of, that's what I want to actually do with this lecture is, yeah, I had this thing on, you know, quantum behavior. That doesn't show much. I don't know why. Oh yeah, here we have it. Where I talk about it, and it's sort of, you know, I give a classical explanation. Well, here we have the electron interference. That's sort of, yeah, maybe to say that sort of the classical thing which Feynman lectures start with is, you know, this interference of an electron with itself when it goes through two slits. I would say, like, you know, just observe when there is only one slit. What we have here. Here we have two slits. What is interesting is once you consider an electron to be some kind of oscillation of charge, you obviously get an interference pattern that very much resembles light interference. What is happening is interesting, but mainly at the edges. But here's sort of the interference between light particles. I did not do much about that. Apparently, yeah, here I have an article on academia.edu where you know, I talk about this classical explanation, and that's where I find that you know, my principles to explain it. Maybe I went a little bit fast. I consider energy, constructive and destructive interference for linearly polarized beam. I wonder where the energy goes, and I say that the energy needs to be conserved, unlike what you have in you know, these theories about virtual particles and stuff in quantum field theory. And I put down here a sort of you know, an explanation in terms of the polarization of the photon, which could be right-handed or left-handed. And as I said now, you know, that needs to be qualified. A photon always has a unique plane of polarization, and that plane of polarization itself can have spin. So this explanation that I have in this paper here is not wrong, but it's kind of simplified, I would say, and doesn't quite catch what I want to say here. What's the what is the thing actually? You know, when you have an incident beam of light and a beam splitter, you know, 50% goes here, 50% goes there. We have a mirror. Um, the A and B are going to talk about it. Comes back. In the second beam splitter, we have constructive or destructive interference, and that means that you know, the light beam either goes all there or there, 1-0 situation, which modern quantum physicists that will say, hey, look, this is quantum mechanics, right? All the lights go into one photon or light detector only. This 1-0 thing about quantum mechanics. And the thing is, what he says, let me very quickly show it. I hope it doesn't get censored. Is yeah, in his chapter 1 of this course, you know, it's about, like, you know, I don't want to talk about electron interference. I'm going to talk about, yeah, this. How does it work when you only have one photon? And then you get a very obscure discussion about, you know, this can only be explained by, you know, attaching some kind of a probability amplitude to the path. This path, that path, this path, that path, then adding and multiplying, you know, these amplitudes. And that's the only way you can explain this weird experiment when you dissolve the incident beam and say, like, okay, it's photon by photon that is moving through these beam splitters. So yeah, that's what I say here, and I'm gonna let you read it. Instructive to think of the incoming beam as a sequence of photons that we send into the interferometer, one photon at a time. And I said then there's a very convoluted logic that says, you really, it's like the photon, this photon that comes in, has like a dual existence in terms of, some kind of wave function that we have here and a psi function here, and depending on the phase of these two functions, we will have constructive or destructive interference. And because the phase has a certain frequency and velocity, it really depends on the distance. You move this thing a little bit out, or you a little bit up and down, and then suddenly it goes here or it goes there. It's utter nonsense, I'm sorry to say. The Emperor has no clothes. That's another text of mine. But the principles of a classical explanation here would really be that you have an incoming light beam, which is circularly polarized. And again, I cannot repeat that enough. Is a circular or elliptical polarization of a light beam. Is when you have an oscillation, two oscillations that you superimpose on each other and are not in phase. So if you're talking about one photon has only one phase, a definite phase. I will talk about uncertainty a little bit later, and what it is actually. But the beam is circularly polarized, so it means we have what I call a lot of photons with different phases, and these photons can be at the same spot, the same XYZ position at a specific time t, or they can be indeed sequential. And then we talk about the electromagnetic wave rather than individual photons. You do have something like that where your X component and your Y component of the electric field have indeed that phase difference that you have when it's a circularly polarized wave, exactly equal to 90 degrees. So when you break that down to one photon only, then it's really the polarization state of that photon combined with its phase that really determines where this photon is going. Maybe it will go here, or maybe it will go there. But the idea that the photon sort of travels through, takes two paths simultaneously, that is nonsense, I'm afraid. I want to wrap this up by saying basically, thing I was told once about 15 years ago. I said, photons have no wave function, and that was by an old nuclear scientist, quite famous. Was posted in Bangkok at the time, and I agree and I don't agree with him. We can sort of usefully associate a wave function that models the physical characteristics of what a photon actually is. What I put here, it is a thing that oscillates in space and in time, and so it has a phase, and that phase will be a function of time, a very simple function, the frequency, and the frequency is given by the energy divided by a Planck's quantum of action, the reduced Planck quantum of action in this case, and so on. So you can associate a wave function, but it's true what he said in the sense that this thing about a linear oscillation is this electric field vector going in and out. That's something you do not catch with wave function which has a fixed amplitude. In that sense, he was right, and I would like to actually revisit the mathematical framework that I put in. I don't have it here. Oh, maybe I do. Yeah, The Emperor Has No Clothes. That was a manuscript of mine. 2019. I would like to rewrite that. It was written a bit in that sense of Boltzmann, bring forward what is true. Write it so that it's clear, defend it to your last breath. The last thing I don't do. I'm just an amateur physicist, so I don't get really upset about things you believe or don't believe. But my chapter on here, the interference of a photon with itself, is very much rooted in indeed attaching a representation of the photon in a wave functional format that may not be appropriate. So I think I will finish with that and upload this. It's been probably one of the most confusing lectures for you. I encourage you to have fun and look at those papers. I got really very encouraged. I think I'm really done. Yeah, there's no other page here. By a lot of I would say likes I got. Principle of quantum physics in my papers. A lot of people are recommending that now. I wrote something on understanding quantum theory, a K-12 level introduction. For the secondary school level, you don't need a lot of math to understand how beautiful it all is. One thing I want to go back to though is because I'm often being criticized as saying you don't agree with anything, right? And that's not true. And I want to show here this thing. This is what Professor Zwiebach writes, where he puts this dichotomy in the famous fifth Solvay conference of 1927. The world's most notable physicists gathered to discuss the newly formulated quantum theory. 17 out of 29 attendees were or became Nobel Prize winners. As said, Einstein was actually one of them, but he didn't get his Nobel Prize for relativity theory, and he got it very, 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 very late. There's quite a controversy on that. I think the same controversy now is a bit about why is it all American and some European um, scientists that get Nobel Prizes? China's building accelerators has contributed a lot, and no Nobel prizes for Chinese or Russians. Okay, that's a rant. But what is said here is Einstein, unhappy with the uncertainty in quantum mechanics, stated this now famous quote: "God does not play a dice." To which Niels Bohr is said to have answered, Einstein stopped telling God what to do. Bohr was willing to accept the laws of determinism, Einstein was not. And so this thing goes on that, quantum physics is, we need to accept that nothing is deterministic, and that was the big mistake of Einstein. And, my position is in between the two, and that's a paper, if you want to read about that. The world is statistically deterministic. Let me go and show you that paper. If you really want to have some kind of easy and fun talk about the dogmas in science, I would say it is to go to this publication. All pre-papers I don't bother to publish in journals. I really love ResearchGate and the ease with which it brings good discussions and questions. Where is it here? Nuclear finite ontology. I write about that. We'll see it, but I have a paper on sort of these big questions that you have, and it boils down to indeed, who are we? What can we understand? What is the universe about? Yeah, I don't see it, but it's statistical determinism, and I should find it here. I wrote too much stuff that I need to wrap up like in one consistent book, but that's a retirement project. No, I don't have it. In any case, there should be a more philosophical paper among these papers that you can understand without too much math, without too much thinking in terms of these very complex geometries that you have in physics. Here, that's the one. The uncertainty principle, statistical determinism, and free will. That's really a paper I wrote last year. I'm not sure if it has a lot of reads, probably not. No, it doesn't have a lot of reads. But that's a paper I like, and because it sort of I said it brings some fun back in and wonder into when you think about who we are, what we can know, and it sort of flattens out your ego, I would say. And that will be it. And I will upload this and see how it goes. Maybe I will erase the video in a few days from now because I realize it's really a lot of spinning. I wish you a very nice evening. And again, greetings from Brussels. The Brussels Pride show was marvelous and the weather was beautiful. Bye.